Well, hello there, guys. I have something to show you. Here's another one of those janky physics demos where Miss Wilson holds a computer awkwardly over like a small demo table and hopes that you can see okay. Okay, here we go. If you look here, what I have is I have a little circuit that is connected up here. It's literally just a battery over here and some wires and some little compasses. Now here's what I'm going to do is I'm going to, if you look, oh, that's another demo. We'll get to that one in a second. If you look right here, I have a little switch. And what I'm going to do is I'm going to flip that switch and current is going to run into the wire. And when I do, I want you to pay very close attention to these compasses here. I'll hold this one right here so that you can see the compass. And I want you to see what happens when I flip the switch. Are you ready? Okay, here we go. Oh gosh, well, I really did just like throw everything all over the place. Let's watch this one right here. Can you see that little compass? Like at all? Maybe, maybe not. Okay, ready? Here's another compass for you to watch. And actually, I'm going to see if I can move it like this. I know, again, Miss Wilson, can you please have a less janky physics demo? I know, it's really tragic. Okay, ready? Here we go. 3, 2, 1. Oh, that one did not do very good. Let's try again. 3, 2, 1. It doesn't do well when I'm holding it up like this. Otherwise they just get stuck where they are. Oh, see, it's just so hard for you to see. This is why I shouldn't do demos this way. It's just absolutely terrible. But here's what you should see, ideally, is what you should see is that when you flip the switch, the little compass moves a little bit. Now, we know that compasses are essentially magnets, and that magnets move if they're responding to a magnetic field. Here's a true story. Once upon a time, there was a guy by the name of Christian Ørsted, and Christian Ørsted was a science teacher. And he had just been doing a unit on electricity, very similar to the way that we did a unit on electricity. And he sat down at his table and he was showing his students a little bit of a circuit sort of situation. But he also had all these compasses just laying around on his desk. And when he showed them this demo, when he flipped the switch, he noticed that his compasses got tweaked when he flipped the little switch. And he said, that's interesting. And so then he did it again, and he noticed once again that the little compasses got tweaked when he flipped the switch. And then he did it again and again, and he noticed that every single time his compasses would move when he flipped the switch. And he said, compasses only move in the presence of a magnetic field. And so he concluded that electricity was creating magnetism. And that's our topic of the day. How can electricity make magnetism? I'm going to go ahead and pause here, get a little bit resituated, and then we'll go ahead and talk about it. Okay, today we're talking about B fields created by moving charges in Ampere's law. Here's the main idea. The main idea is, as you know, all magnetism is created by moving charges. Moving charges is what makes magnetism happen. Well, if you have a wire, oh gosh, that is not what I wanted. If you have a wire, wait for it. Oh wow, we are just so delayed right now. Try again. If you have a wire, then you have little charges that are moving through that wire. That's what current is. If you have a wire that has current in it, then you have little charges that are moving in that wire. And if you have charges that are moving charges will create a magnetic field. The same way that there's a gravitational field just because something that has mass exists, the same way that there's an electric field just because something that has charge exists, if you have a charge that is moving, that creates a magnetic field. And so little charges moving in the wire will create a little magnetic field. That is Ørsted's principle, named after Christian Ørsted. Ørsted, ooh, let me check my spelling. That is Ørsted's principle. Named after Mr. Ørsted, who noticed that his compasses were moving as he turned on the switch, as he flipped the switch for the wire. I seriously am going to check my spelling here because I don't really know how to spell anything. Oh, yes, this is embarrassing. There is no A. Oops. Sorry, Mr. Ørsted. I mean no disrespect to your good name. Ørsted's principle. Now, we're going to talk a little bit about the kind of magnetic field that we see that gets produced by these little charges in a wire. But before we do, let's talk about the other kinds of fields that we know. We know that gravitational field strength is equal to the force created by the gravitational field divided by the thing that experiences that force, a little chunk of mass. We also know that the electric field is equal to the electric force that is put on a little charge divided by the charge that experiences that force. Likewise, a magnetic field is equal to the force that is put on the thing that causes that field, which is a little moving charge, which we write as QV. Q here means charge, V here means velocity. So you multiply the size of the charge by the velocity of that charge, and that gives you the strength of the magnetic field. And if you had to use one letter to represent magnetic field strength, you would, of course, choose the letter B. Yep. And so, wow, that is not a very good subscript. And so we often call magnetic fields B fields because we represent magnetism with the letter B. Please don't ask me why I was not on that committee for making that choice. So here's one equation for the strength of the magnetic field, is that it's the force created by the magnetic field on a little moving charge that happens to wander into that field. You can see the parallels to these types of field strength over here, and you can see how it really just matches up so nicely. Here we have the force divided by the thing that causes the force divided by the thing that causes the force divided by the thing that causes the force, which is a moving charge. So that's a small equation for you. Let's check our units here. The units of magnetic field strength are going to be newtons divided by coulombs times meters per second, or in other words, Newton seconds over Coulomb meters. But all the good people of the world got very tired of saying Newton seconds over Coulomb meters, Newton seconds per Coulomb meters, Newton seconds per Coulomb meters all the time. And so they said we need a new unit, and the new unit that they used is Teslas. Just like the fancy car, except not at all like the fancy car. It's a capital T Tesla, named after Mr. Tesla himself. And another unit that you'll sometimes see, another unit that you'll sometimes see is a Gauss. Gauss is spelled G-A-U-S-S, is a Gauss. Which we represent with the capital letter G. The reason why we sometimes use Gausses instead of Teslas is because 1 Gauss is equal to 1 times 10 to the negative 4th Teslas. And that is because a Tesla is actually like, you're never going to see a magnetic field that has a field strength of 1 Tesla. If you're seeing something that has a magnetic field strength of 1 Tesla, like, you should be concerned for your life. That thing is crazy. We don't normally have magnetic fields that are that strong. A Tesla is a huge field strength. So most of the time, you'll see things in like micro Teslas, like it's a teeny tiny fraction of a Tesla. Or here, we simplify it by saying 1 times 10 to the negative 4th Teslas is a Gauss. So that it just makes your units a little bit more manageable. So there's a little bit on units, there's a little bit on magnetic field strength. And now, what we're going to do next is we're going to talk about that particular magnetic field that is created by a current-carrying wire. Now, here you have an equation for a very general equation for field strength, where field strength is the force exerted on a little moving charge that happens to wander into the field. Notice this is the moving charge that wanders into the field, not the moving charge that creates the field. So this is a very general equation, but if we wanted to know what is the magnetic field like from a wire, well then we'd have a whole other set of equations and a whole other set of principles. Here's what we're going to do today. First, we are going to talk about the direction of the magnetic field around a current-carrying wire. And then we are going to talk about the strength of the magnetic field around a current carrying wire. We're going to start by talking about direction, and actually I'm going to pull up a new tab here so that we can do this all afresh as a new topic, and I'll even change my color. I know, crazy. Okay, so here is a wire, and this wire is carrying a current. We'll say that this end of the wire is connected to the positive end of the battery, and this end of the wire is connected to the negative end of the battery. Now, you do have to be able to know which way the current is going to flow. We say that the current always flows from the high potential place to the low potential place. It always flows from the positives to the negatives. Of course, that's not the way that the electrons are actually going. It's the way that the protons are going, which gets all confusing, but we can really treat it as if protons are actually going this way. So we can say that positive charge is going this way. That's the direction of our current. Now, because charges are moving and all magnetism is created by moving charges, you're going to get a magnetic field around this wire. In the magnetic field, when we talk about direction, the direction of the magnetic field is always going to be in a circle around the wire. It's going to encircle this wire. Now, there are two ways for this magnetic field to encircle the wire. Here is a pencil, but pretend it's a wire. Wait, let me make this a little bit bigger so that you can see it. Okay, here is a pencil, but pretend it's a wire. Let's suppose that this end right here is connected to the positive end, and this end right here is connected to the negative end. So the current is flowing this way through this pencil. If current is flowing this way through this pencil, there's going to be a magnetic field that goes around this pencil. But do you see that this magnetic field could go around this pencil this way, or it could go around this pencil this way? In order to figure out which way the magnetic field is going, we use a very, very technical strategy that we call the right-hand rule. Here's how the right-hand rule works. Go ahead and give a thumbs up, like you're having a great day. Your thumb is going to represent the direction of the current in the wire, and your fingers then will naturally curl in the direction of the magnetic field. If you wanted to, wait, hang on. Oh no! Okay, wait. Wow, sorry, I'm just making a mess over here, but it's worth it. Sharpie. You can imagine that your fingers, tattoos for science, you can imagine that your little fingers are like a little arrow that is pointing in the direction of the magnetic field. So what I do with this pencil here is the current is going this way. I pretend like I'm grabbing the wire like this in my fist, and the direction of the arrow here that you see is the direction of the magnetic field. So the magnetic field would go this way around the wire. In order for the right-hand rule to work, you do have to use your right hand. If you use your left hand, you will get absolutely the wrong answer. So you do need to use your right hand. Thumb points in the direction of the current. Your fingers curl in the direction of the magnetic field. Let's go ahead and try it. For this particular picture, I have current that is going this way. And so when I pretend, I take my right hand, I'm going to pretend to grab this wire in my hand. Now, oh wait, I have to do it backwards for you. Okay, I have to pretend to grab this wire in my hand. So I'm going to take my thumb and I'm going to point it in the direction of the current. The current is going, whoop, this way. So I grab it like this. That means that then when I'm looking at this thing, the current, or the magnetic field goes under the bottom of the wire, up on the back side of the wire, and down on the front side of the wire. I can imagine as if I'm grabbing this thing in my little hand which way the magnetic field is going to go. So here's how I draw this. I like to draw the part that's going on the back side as a line with a gap in it, and then the part that's going on the front side as a solid line. I'll show you what I mean. I'm looking at this and I'm saying, okay, on the back side, the magnetic field is going to go, whoops, let me try again. On the back side, the magnetic field is going to go up, but then it's going to curve back down around the front side going down, and it's going to make little loops like this. So it'll go up on the back like this, and down on the front like this. Up on the back like this, and down on the front like this. And this little wire will create little magnetic field lines going all around it in little circles this way. That's the idea. Here's how we normally like to try one of these problems, is we normally like to say something like, what would be the direction of the magnetic field at point P here? Let me choose a point P. At point, sorry, I gotta get rid of this thing. Yep. Okay. Oh, nope, redo. Okay, at point P. We like to say, what would be the direction of the magnetic field at point P? And here's how we do it. We say, okay, well, I use my right hand rule, and I pretend like I'm going to grab this thing in my hand. And so when I do, wait, sorry, I'm so sorry. Okay, nope. Oh gosh, too far. So when I do, I put my thumb in the direction of the current, my fingers curl in the direction of the magnetic field, and I see that when my fingers hit point P as they're wrapping around that wire, my fingers hitting point P will be traveling into the page. Does everybody see that? Or into the screen. That means that the direction of the magnetic field at point P is going into the screen. Now, here's where it's very, very hard to draw something going into the screen. It's easy to draw going down on the front side. It's easy to draw going up on the back side. It's very hard to draw something going into the screen or out of the screen because we're not very good. Well, I'm not very good at drawing 3D. Maybe you are, and that is super awesome for you. But myself and a lot of other physicists find that they had trouble with that, so that we came up with a whole system for how to draw things going into the board or out of the board. To draw something that's going into the board, we use a little, we use a little X to represent going into the board, or into the page, or into the screen. So directly away from you is a little X. And then coming directly towards you, we use a little dot to say out of the page, or out of the board, or out of the screen. That means coming directly at you. The way that I remember this, and the way that I was taught to remember this, and it's just such a glorious analogy, is to say that it's kind of like a little arrow. If you are seeing, if I had a bow and arrow here, and you were looking at the little tip of the arrow, you would see a little tiny dot, and you would say, that arrow is facing towards me. And so we use a little dot to represent something that is facing towards you, that is coming out at you. We use a little X because it's like if I were to hold my arrow and then turn it around, what you would see is you would see the feathers on the back of the arrow, making sort of an X-like shape. So the X means the feathers. That means that thing is going away from you, or it's going into the page away from you. So here's the idea. Here, when I look at this thing and I use my right hand rule, I say, okay, my fingers curl up on the back side, down on the front side. When they hit point P, they are going into the page. So I'm going to draw a little X here representing that the magnetic field is going into the page. That actually gives us a whole new strategy for drawing the magnetic field around this wire, because we could draw it, oh gosh, that's so crooked, because we could draw it like this. If this is that's still crooked, but it's okay, we're going with it, team. Okay, if this is the positive end, this is my negative end, here's my current is going this way. I could draw my magnetic field as a series of dots and arrows. Here's how I would do it. I would say, okay, up on the top side of the wire, my right hand rule says that the magnetic field is coming out of the page. Oh gosh, that is not what I wanted. Sorry. Up at the top of the wire, my right hand rule says that the magnetic field is coming out of the page at me, so I'm going to draw a little dot, but then when it gets down to the bottom, it's going back into the page, so I'm going to draw a little X to show that it's going back into the page. Then, right next door, same thing, you're going to have a little bit of magnetic field coming out of the page, and down here, the magnetic field's going back into the page, and so on and so forth. So instead of drawing it as a series of arrows on the front side and on the back side, which can get very confusing to draw, I can draw it as a series of dots and X's, dots being on the top of the wire, it's going into the page, or it's going out of the page, and on the bottom of the wire, it's going into the page. So that is another way to draw the magnetic fields. Let's go ahead and try a practice problem. Here's one for you to try to see how you can do. Let's say that I had a wire like this, and this wire was connected to 6 volts. Actually, wait, I'm going to go. Let's say, oh no, too much. Let's say it was connected to 0 volts over here to the ground potential. Let's say it was connected to 6 volts over here. That was the potential over on this end. Can you figure out which way would the direction of the magnetic field be going? Please draw a picture, draw a diagram in your notes. Draw 2 diagrams, one using the arrow method and one using the dots and X's method. Okay, in order to even start this problem, you need to know which way the current is going. The current is going to go from high potential to low potential always. So we say that the current is going to go this way in the wire. Then, if my current is going this way in the wire, I take my thumb, I point my thumb in the direction of the current, I pretend to wrap my fingers around this wire like this, and here's what I get, is I get a magnetic field. We'll change out my color for my magnetic field. I get a magnetic field that is going up on the front of the wire and then down on the back of the wire. At the top of the wire, you can see it's going into the screen, and on the bottom of the wire, you can see it's coming back out of the screen. So a few different ways to draw this. First, I could say, okay, on the front side, I'm going up, the magnetic field is going up. Then on the back side, the magnetic field is going down. Here, once again, on the front side, the magnetic field is going up. On the back side, the magnetic field is going down. That's one way to draw. Another way to draw it is to say on the top, it's going into the page. And then on the bottom, that magnetic field is coming out of the page. So there you go. Here's another example to try. Try this one. Say that we have a wire, and that wire is coming straight out of the screen, going straight towards your face. So let's say that here's like a side view of the wire. So you're like looking straight at the end of the wire right now. And let's say that the current, I, is coming out of the board, or out of the screen, or out of your paper towards your face like this. Then, could you label where the magnetic field is, or what the magnetic field looks like? You should say, sure, Miss Wilson, here's what I would do. I would say, okay, the current is coming out of the page towards me. So you take your right thumb and you would point it towards yourself, just like this. Then you'd say, my fingers are going to curl around this wire. The way that they're curling when your thumb is pointing towards you is going to look something like this. And your fingers are going to curl counterclockwise around this wire. Then, here's another perspective. Try another one. What if you had a little wire like this with the current going into the page? Could you draw this one? You say, sure, no problem, Miss Wilson. Here's what I would do. I would take my right hand, I'd point my thumb in towards the page or in towards the screen. I would see that then my fingers curl from here around this way. And so you would say, well, it appears that the direction of the magnetic field is going this way. It's going clockwise. Notice on these ones, the magnetic field is going around in circles, and I should really make that a complete circle. But notice that in these ones, the magnetic field is going around in circles. I don't need to use dots and X's because nothing is coming into or out of the board except for the current. There are a few examples with a single wire. Let's see if we make it a little bit more interesting, if we can make this wire not as straight. I'm going to pull up a new little page here. One second. Okay, here we go. So, oh, whoops, let's get that out of the way. Okay, so let's try something a little bit different now. I'm going to go ahead and change this right here. Let's try a wire that is curved, something with a little bit more of a challenge here for you. Okay, wait 1 second. I gotta undo that. Computer, you can do it. Yes, way to go. Okay, here we go. Let's say that we had a wire that was curved. Whoa, that is fine. Okay, wait, here, this one's better. Okay, here's a wire that's curved. Let's say that I added this, or I put this end of the wire on a positive terminal of the battery, and I put this end of the wire on the negative terminal of the battery. could you figure out the direction of the magnetic field at the center of this wire? Well, here's what I would do. First, I would say, okay, let's take a look. I'm going to use my right-hand rule, but before I can even do that, I have to determine the direction of the current. I know that current is going to go from positive to negative, and so it's going to go like this is going to be my direction of the current, and it's going to go in a little loop-de-loop type shape. So it'll go up on this side, then down on this side, then back over here on this side. And I think, okay, I want to know the direction of the magnetic field at the center. Well, my thumb is going to point in the direction of the magnetic, or in the direction of the current, but the current direction is changing. Let me show you here. Whoa, okay. Let me show you how we do this. Here is a loop of wire. Let's say that this, I want to make it the same as what I'm seeing here. Okay, let's say that this end is connected to the positive end, and this end is connected to the negative end. Then here's what I would see. I would see that the current would travel along this wire here. It would go up this little loop-de-loop and then back down this little loop-de-loop and then back on this side. When I grab the wire with my hand, here's what I'm going to see. I'm going to start here. When I get to this loop-de-loop here, do you see that my thumb points in the direction of the current? My fingers point through the loop like this in the center, and then they curve around the loop and point back at me like this on the outside. Then when I get to here, same thing. My fingers point through the loop in the middle, they curve around and point back towards me on the outside. And same thing all the way around this loop. As long as my thumb is pointing in the direction of the current, my fingers point through the center, out of the page towards you, and then they point back towards me this way. So here's how I would draw this on this piece of paper, or on my screen. You would draw this on your piece of paper because you have a piece of paper. You would say that the current, when it goes through this loop, is going to come out of the loop towards you here and here. Oh wait, let me draw this with my other color so that we can keep things clear. Okay, wait 1 second here. Just a moment, please. Okay. Color transition time. Okay, here we go. 1 second. Okay, so we'd say at the center of the loop, it's coming out towards you, like this, where my little dots represent something that is coming towards you. Then outside of the loop, here and here, and here and here, it's going back into the page or going away from you. And that's the idea. Now here's a question. If I were to ask you, where is the magnetic field stronger? Is it stronger inside the loop or outside of the loop? You would say it's for sure stronger inside of the loop, because the loop is going to force all the magnetic fields to kind of come together to go out through the loop. But then on the outside, they're going to be a little bit more spread out. So the magnetic field is way more concentrated. It's way stronger in the middle of the loop than on the outside edge of the loop. Let's try another practice problem here. Say that you had another loop, and this time we're going to say that this end is the negative end and this end is the positive end. Could you find the direction of the magnetic field in the center of the loop? Very common question, actually, that gets asked is, hey, could you find the direction of the magnetic field at some point that we call point... Oh, gosh, wait. So sorry, team. Allow me to just get rid of all of that mess. Could you find the direction of the magnetic field at some point that they say is point P here? If they say find the direction of the magnetic field at point P at the center of the loop, the point here does not mean that point P is coming out of the page. It's just a point showing where point P is. So can you please try to find the direction of the magnetic field the direction of the magnetic field at point P? Now, most of you would probably say, okay, well, I could do this problem just by knowing that it's probably going to be the opposite of this one since you just switched the direction of the current, which is true, but make sure that you can use your right-hand rule to do it. Here's what I would do. I would look at my little loop. I'd say, okay, we flip-flopped now, so now, sorry, I'll make this a little bit bigger. I would say, okay, we flip-flopped now. So now this over here is my positive end, and this over here is my negative end. If I'm going from positive to negative, when I grab this loop, notice my fingers point through the loop into the loop when I'm going on the way up, and then they point out of the loop or out of the page on the outside. So we go out of the page on the outside into the page on the inside. When I draw this on my little diagram here, and oh, I lost my little P, my little point P got destroyed. Okay, when I draw this on my diagram, I show that inside of the loop, it's going into the page like this, and I represent it with little X's. Then I say outside of the loop, it's coming out of the page, and I represent that with little dots all around. If I asked you what's the direction of the magnetic field like at point P, you would say, well, Miss Wilson, it's probably going into the page because all of the magnetic field in the center of the loop is going into the page. So that's how you would describe it. Those are some loops. Let's go ahead and try something different. Now we're going to try a bunch of loops. So, oh my, oh me, oh my. That is not what I wanted. So what if you had, sorry, I'll shrink this down. What if you had not like just one little loop like that, but what if you had a wire and you took it and you did a loop and then you did another loop and then you did another loop and then you did another loop until you did another loop and then you did another loop until you had a bunch of loops of loops. Well, if you did a loop of loops, what you would have is you would have something that looks like this. And I'm going to draw it once again in blue. You would have, and I'm actually going to draw like, pretend I put all these loops around like a bar or something because that can be helpful for my drawing purposes. So imagine that I had a loop of wire that went like this. I started on the back side and then I looped around the front side like this, and then around the front side like this, and then around the front side like this, and 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 there. Now I have a bunch of different loops. Here's a question. What would the magnetic field be like through the center of all of those loops? Interesting. Let's try it. Let's suppose that this end is attached to 0 volts and this end over here is attached to 6 volts. Like this. Okay, well then here's the first thing that I'm going to do is I'm going to determine the direction of the current. Well, I'm going to say that the current is always going to go from high potential to low potential. So it's going to start by going up here, then it's going to go up on the back side, and then when it curls around, it's going to go back down on the front side. Then it's going to go up on the back side again, back down on the front side, up on the back side, down on the front side, up on the back side, down on the front side, up on the back side, down on the front side, so on and so forth, and it'll always be going down on the front side and up on the back side. Now, here's what I have. Essentially, do you see how this picture is basically a bunch of loops, and I'm going to show you my loop here. It's basically a bunch of loops, but now these loops are, whoa, sorry. Go away. Why are you being obnoxious? Okay. Now, these loops are, instead of facing you like this, these loops are now on their side. But it's the same thing. It's just a normal, regular loop. Here's what you see, is you see that the current is going up on the back side and then down on the front side. If you took your hand and you held a little sideways loop like this, and you put your thumb in the direction of the current so that it was going up on the back side and down on the front side, here's what you would see, is you would see that for one little loop, if the current's going up on the back side and down on the front side, when I grab this wire, when I grab on the inside like this, my fingers are pointing this way. Then to the right or left is very hard for me right now because I'm standing opposite you. To the right, I think. Yeah, I'm going to say to the right. The magnetic field would go through the middle to the right. Then, when my fingers curl, they would curl around like this and curl back going to the left. But in the center, do you see how as long as my thumb is going up on the back side, down on the front side, at the center of the loop, my fingers would always be going to the right. When I draw it in this little picture here, I will draw that the magnetic field, hang on one moment please, the magnetic field from this little loop is going to the right. Because when I use my right hand rule, my fingers are always going to be curling towards the right in the center of the loop. Well, then if I look at this next little loop here, the next little loop is going to be the same thing. You have current going up on the back side and down on the front side. So my magnetic field, once again, is going to be going to the right inside of the little loop. So it's going to be going this way, once again. And same thing with each of the rest of the loops. They're each going to create a little magnetic field going to the right. which means all of these little loops together are going to create a magnetic field going to the right this way on the inside of the loops. Then, if you look on the outside of the loops, my fingers curl back around the other way, and now my fingers on the outside of the loop are always pointing to the left. And so I would see that the magnetic field would go to the right on the inside, and then, oh gosh, no need to be extreme about it, and then to the left. Sorry, I can't draw in a straight circle. That is a crazy sentence even. I can't, it's really, really hard to draw nice curves here because I actually can't see where my mouse is making the mark until it's already done it. Okay, so that way around the outside, and it would go back this way around the outside like this, and this way around the outside, and this way around the outside like this, and you would get a little magnetic field that looks like this. Hey, when you're looking at that, you say, wait a second, Miss Wilson, that looks an awful lot like a bar magnet. Did you just use electricity to create a bar magnet? Yes, absolutely. And here's what we would say looking at this bar magnet is that we would say it appears that this side looks a lot like a north end of a magnet, and this side looks a lot like a south end of a magnet. This device, just a coil of wires, is so significant because we can actually make a magnet out of electricity. And it's so significant that we call it a solenoid. A solenoid is just a coil of wires that if you connect it to electricity, it turns into a little magnet. Now, if you wanted to make this magnet even stronger, here's what you could do. You could take a little iron core, and you could put this little iron core in the center of all the loops. If you put the little iron core in the center of all the loops, oh gosh, I was trying to color it in, but that was a terrible idea. I take it all back. I just ignore that I ever did that. If you put a little iron core inside of the center of all the loops, well then all the dipoles, all the domains inside of that iron core would get all lined up with the magnetic field that's being created by the solenoid. And so you would have a magnetic field, not just from the coils of wire, but also from the iron core on the inside. This would make an even stronger magnet. So when we take a solenoid and we put a little iron core inside of it, we call that an electromagnet. An electromagnet. An electromagnet is a solenoid with a little iron core inside of it, and it's literally a magnet that you can turn on and off. It's a magnet created by electricity. Let me show you what it looks like, but I do have to go grab it, so 1 second. Okay, I decided to just move the whole computer. Okay, so here's what we have. This is an electromagnet. You can see I have here, it's literally just like coils of wire, and then in the center here is a little iron core that you can take in and out. That's it. Then I have here these little wires which can connect to my little electromagnet like this, and then it's connected to a battery. Now, I didn't get like a switch over here, so I'm just gonna have to like attach it to the battery and then detach it from the battery. But here's what you see. I have a little pile of paper clips. And now you can see that when I take this iron core, and I hold it near the paper clips, no dice, no magnetism happening here. Very, very boring demo. But if I take this electromagnet and I connect it to the battery like this, now this thing is going to act as a magnet. And you can see it does a very impressive job of lifting up some paper clips here. Disconnect this string from the battery and check it out. Paper clips all fall off, except for a few, since this iron core still has its domains lined up a little bit. But if you knock them off, you'll see that it loses all of its magnetic abilities. Connect it again, and once again, it can pick up the paper clips. This is an electromagnet. An electromagnet is super, super useful to us. Students have asked me before, hey, Miss Wilson, what's the strongest magnet that we've ever made? It's an electromagnet. Because an electromagnet is super easy to make really strong. All you have to do to make a really strong electromagnet is to add more coils or increase the current. Do you see how that could be super easy to do? Like if I just put some more coils around this thing, or if I made the current a little bit stronger, this magnet would be even stronger. We use electromagnets to make permanent magnets. If you have a permanent magnet that's really strong, you know that in order to make that permanent magnet, you have to let it sit in the presence of a magnetic field for a really long time. Where did that magnetic field come from? It came from an electromagnet. An electromagnet can make such a strong magnetic field. So it's incredibly, incredibly useful to us. The type of magnets that we use to like pick up cars are electromagnets. So there's a little bit on electromagnets. I'm going to pause the video here and then go ahead and get resituated once again. Be right back. Okay, welcome back. You'll see here that I have drawn a new electromagnet. This time I have this end connected to the 6 volts of potential, this end connected to the 0 volts of potential. Can you please try to figure out which end of this electromagnet would end up being a north pole and which end of this electromagnet would end up being a south pole? Go ahead and try it. You probably should pause the video here and figure it out. Now, some of you smarticle particles just said, well, Miss Wilson, it's just going to be the opposite of what I saw over here because you just flipped the 2 potential sides. Yes, that's very true, but make sure that you can use your right-hand rule to do it. Here's what you would say. You would say that the current is going from 6 volts to 0 volts. So it's going to go down on the back side and then up on the front side. And up on the front side here, down on the back side, up on the front side, and so on and so forth for the whole course of this wire. You take your little wire, you say, okay, I'm going to imagine myself grabbing these little wires. You say, I'm going to do it with my thumb pointing up on the front side. On the front side, then I can see, and I'll make this a little bit bigger for you. You can see that on the front side, my fingers are going to go to the left outside. I don't know my lefts and rights. I'm so sorry. Like, I kind of do, but I also kind of don't. But they're going to go this way on the outside of the wire. And then back in the wire, it's going to curl back around and go this way. So you're going to draw that on your little diagram here. You're going to draw, change my color. You're going to draw that if I'm going up on the outside, then my fingers curl this way. Wait, did I do this all backwards? Hang on. Whoop, whoop, whoop. Did I do my other one backwards? Oh gosh, now I'm getting all confused in my brain. Up on the front side, down on the back side. I think I might have done the other one backwards. Wait, I did up on the back side, down on the front side. Oh no! Did I do my whole other one backwards? Oh, that's so embarrassing for me. Wow. Oh gosh, and there's the bell. Okay. Oh man, I just feel terrible right now. I hope you all are recovering okay. Luckily, you're like very smart people, so I think your brains will be mentally flexible enough to like rewire your neurons. Oh my gosh, this is awful. Okay, here's the idea. I don't know how I got that so backwards. I think I maybe just drew it backwards. Okay, like truly, here's my problem is that like when I do the thing over here in real life, it then flips the image when I do it on the little on the little screen here. It's like backwards of what I'm doing in real life, and that is just like my like brain that struggles with like all kinds of directional things is just like flipping in circles right now. On the other one, I should have said that the like direction of the electric field on the inside is going to be that way. Wait, but then on this one, it's going to be this way. Okay, I did do it right on the other one. Wow, I'm so sorry you've had to sit here and listen through all my mental processing. I just can't get the picture that I'm doing here to correspond to what I'm thinking there. So I'm just going to do it with the picture that I see there because that's easier for me and I won't get confused. So here's what I'm doing. I'm imagining that I'm grabbing those little loops. I'm grabbing them with my thumb pointing up on the front side, my thumb pointing down on the back side. So my fingers on the inside of the loops are going to point this way. Then on the outside of the loops, they'll curve back around this way. You probably like already can see like all the things that I'm doing wrong. But okay, so up on the front side, so my fingers on the inside are going this way when I grab that little wire. So I grab that little wire and I see that my magnetic field is going, oh, not like that, is going, not like that. I can draw a straight line. I can draw a straight line. I believe I can draw a straight line. It's going this way on the inside. And if it's going this way on the inside, that means we'll end up with a little north over here and we'll end up with a little south over here. Hey, like little like sneak peeky truth about a solenoid. The truth is that solenoids actually don't really have magnetic fields significantly outside the edges here. We drew it that way. If you want to hear more about why that's true, please come ask me. I'd love to tell you about it. It makes it very nice for seeing kind of the bar magnet situation, but The like real true scientific answer is to say, well, it's going this way on the inside and it points to the north over here. That's one way to do your right-hand rule for electromagnets. There's actually another way to do the right-hand rule for electromagnets, and here's the other way to do the right-hand rule for electromagnets. The other way to do your right-hand rule for electromagnets is to take your fingers and to curl them in the direction of the current. Now, this is opposite of what we do, and I don't always love to teach this trick because this trick can be more confusing than helpful. But for some students, it's very helpful. So here's the idea. Is that normally your thumb points in the direction of the current and your fingers curl in the direction of the magnetic field. But if your wires are curly, then you can use your fingers to curl in the direction of the current and your thumb will point in the direction of the magnetic field. So on this little wire here, I point with my fingers pointing up on the front side and then down on the back side like this. And if I go up on the front side, down on the back side, then my thumb will point towards the north pole of that little electromagnet. Make sure that makes sense to you. If it doesn't make sense to you, don't use it. If you like it, great, use it. But only use it if you can keep it straight. So use all rules responsibly. And that's a little bit on electromagnets and the direction of the magnetic field. We have one last topic for today. Now that we've talked about the direction of the magnetic field, we've talked about how to make electromagnets. The last thing that we have to talk about is how you can actually find the magnitude of the magnetic field coming from a wire. So we'll add one more drawing here. If you want to know the direction of the magnetic field, you can use the right-hand rule. But if you want to know the size of the magnetic field, then you have to use Ampere's law. Ampere's law is a very specific equation that will give you the strength of the magnetic field coming from a wire. It doesn't work for like just any magnetic field anywhere. You can't always use this equation. You can only use this equation for a long, straight current carrying wire. The truth about Ampere's law is that Ampere's law, the version that I'm going to teach you here in this video, is actually a much shortened down, simplified version of the more complex Ampere's law. The more complex version of Ampere's law involves a surface integral, which we won't really get into here, but it says that basically, well, it basically looks like this. So that's the more complex version. We won't be doing that version today. Instead, we'll be doing a very, very simple version. But because this is the very simple version, you can only use this version under the following conditions. The only time when you can use this version of the law is if the following statements are true. This is Ampere's law for a long, straight, current carrying wire. That means the equation that I'm about to show you will give you the strength of the magnetic field if you're a certain distance away from a wire that has current in it that is long and straight. If you have a swirly curly wire, it's not going to work. If you have a very short wire, it's not going to work. If you have a wire without any current in it, well, then you wouldn't have any magnetic field from that wire, so that would be completely useless. So here's the idea. The idea is if you have a wire and that wire has some current in it, then there are little charges that are marching all along that wire in the direction of the current. Now, here's the truth. We know that actually in reality, the current is going the opposite way that the electrons are marching, but because we defined everything based on the way the little positive goes, as long as you use your right-hand rule as according to the direction of the current, everything will work out fine. But here's the idea. If you wanted to find the strength of the magnetic field, well, first you'd have to talk about where you want to find the strength of the magnetic field, because there are a few points that you could look at here. One thing that you could say is you could say, well, I want to know the strength of the magnetic field right here. And that would be an option. You could find the strength of the magnetic field at point P. But you could also say, I want to find the strength of the magnetic field at point P out here. Well, then why don't you have two different strengths? Here's the idea, and this should be pretty intuitive to you. The closer you are to the wire, the stronger the magnetic field is going to be. So we have to talk about how far away from the wire we are. We use the letter R to talk about how far away from the wire we want to measure the strength of the electric field. Oh, wow, I said electric field, I mean magnetic field. This means that the equation, Ampere's law, for the strength of the magnetic field is going to depend on two things. First, it depends on the current, And second, it depends on your distance away from the wire. Ampere's law looks something like this. We say that the strength of the magnetic field is equal to mu naught I over 2 pi r. And this equation is, of course, worthy of your bag of tricks. Here's what the equation is saying. Mu naught is a constant. We'll call it the magnetic constant. Another way of talking about it is it's the permeability of free space. So it's equal to 4 pi times 10 to the negative 7th Tesla's meters per amps. Just a little constant here. The magnetic constant, or the permeability of free space constant. I is current, 2 pi, and R is your distance away from the wire. It is not, let's be very clear, the radius of the wire. It's the distance away from the wire. Now, here's what Ampere's law says. Ampere's law says that the strength of the magnetic field increases as the current increases. That should make sense to you. If you have more current running through the wire, you have more little charges that are moving even faster. And if you have more fast-moving charges, then you would imagine that the strength of the magnetic field would increase. Also, it says that as you get further and further and further away from the wire, as R increases, your distance away from the wire, that magnetic field strength is going to get less and less and less. That should make sense to you. It's the same thing with any old magnet. If you get further and further and further away from the magnet, then the strength of the magnetic field decreases. Last, this 2 pi should make some amount of sense to you, because isn't the magnetic field shaped like a little circle? And if the magnetic field is shaped like a little circle, it would make some degree of sense that you would have a 2 pi hanging out in there. So that's Ampere's law. We're going to do 2 practice problems using Ampere's law. Here's the first one, and I am totally going to make up these practice problems as we go, so we'll see how this really turns out for us. Okay, here's the first one. Let's say that you had a wire that had, oh, I don't like that wire, I'm going to redraw it. Okay, let's say that you had a wire here, and that wire had a resistance of 2.0 ohms. And you put one end of the wire, you connected to the 6-volt side of the battery. The other end of the wire, you connected to the 0-volt side of the battery. And you wanted to know, what is the strength of the magnetic field like at a point P, which was a distance, let's say it was located R equals 0.020 meters away from the wire. It's very close to the wire. Well, let's go ahead and try it. First, if I want to know the strength of the magnetic field at point P, I'm going to write down, let's do strength and direction. Yes, that's going to be great. Okay, if I wanted to know the strength and the direction of the magnetic field at point P, here's what I'm going to need to know. I'm going to need to write down my knowns and unknowns. First, I know that my distance away from the wire is 0.020 meters. I know that my resistance here is 2.0 ohms. I know that my potential difference is 6.0 volts, because that's the difference between the high potential place and the low potential place. And I am looking for B. Well, here's what I know. I know that the magnitude of the magnetic field is equal to mu naught I all over 2 pi r. But here's the problem. I have I know mu naught, it's a constant, I know 2 pi, but I don't, I know R, I have mu naught, I have 2 pi, I don't know I. But luckily, I know delta V and R, and I know something called Ohm's law, that I is equal to delta V over R. This makes it very easy for me to rearrange this algebraically. What I'm going to do is I'm going to plug in delta V times R into this equation. What you should not do is you should not plug in numbers first for I and then plug in that number into your other equation. We always algebraically solve first. Okay, so I have mu naught times delta V all over 2 pi little r times big R. Notice that the capitalization does matter here to keep your variables distinct from each other. When I plug in numbers here, mu naught is equal to 4 pi. Oh, that's a terrible pi. I am just embarrassed by that pi. I am so sorry. Okay, 4 pi times 10 to the negative 7th Tesla meters per amp. That's our little constant. My potential difference is 6.0 volts, we'll say. All divided by 2 pi. My radius is 0.020 meters. And finally, my resistance is 2.0 ohms. Now, some of you little geniuses, being the geniuses that you are, you could just like do this in your head, but I'm a total weakling, and I am going to, wait. I want to do this, but I'm going to grab my calculator real quick. 1 second here. One moment. Okay, and you should get, 3.0 times 10 to the negative 5th. Check your units on that. We are talking in terms of Teslas. And there you go. There's your first practice problem. Not too bad. We did also ask to find the direction. Let's talk about the direction at point P. Well, here's what I know. I know that the current here is going to go from high potential to low potential, so my current is going that way. When I talk about my magnetic field, I'm going to use the right-hand rule. I point my thumb in the direction that the current is going, which I guess is, oh gosh, again, the whole flippy thing. I'm just going to do it my way. I point my thumb in the direction that the current is going. My fingers are going to curl, and they're going to be going into the page at point P like this. Like so. So I'm going to say 3.0 times 10 to the negative 5th Teslas, and then I'm going to say into the page. Brilliant. And there's our problem. Let's try one more. Okay, I have drawn up a series of wires here, and by a series I mean 2. I got 2 wires here. This one we'll call wire 1, and this one has a positive charge up here and a negative charge, positive terminal up here, negative terminal down here, and the current is flowing from positive to negative. The size of that current is 3 amps. Over here I have another wire. This wire has a current of 2 amps. Its positive is right here and its negative is right here, so the current is moving in this direction. The question of the day is, what is the size and the direction of the magnetic field at point P, which is located right here, a distance away from both wires? It's located at a distance R1 away from the first wire of 0.20 meters, and it's located at a distance R2 away from the second wire, a distance of 0.40 meters. Now we have 2 magnetic fields, one from each wire. In order to do this problem, all we have to do is find the magnetic field from the first wire and add it to the magnetic field from the second wire. And that will give us the strength of the magnetic field at point P. However, we have to be very careful here to pay attention to direction. Let's talk direction first. I'm going to use my right-hand rule. When I use my right-hand rule on wire number 1, the current is pointing down. I curl my fingers around that wire. When they go through point P, the direction of the magnetic field from wire 1 is out of the page. It's coming back towards my face. So I say that from wire 1, I get a little magnetic field. I'll do it like this. From wire 1, I get a little magnetic field here. It's going out of the page like this. Now let's look at, oh gosh, so sorry team. We can do it eventually. Okay, here it is. Magnetic field coming out of the page. Now let's check out wire 2. For wire 2, I point my thumb in the direction of the current. I curl my fingers. When my fingers hit point P, do you see that my fingers are pointing into the page? They're pointing away from me, and then it curls back towards me, which means that wire B is creating a little magnetic field going into the page. That means these 2 magnetic fields are in conflict with each other. So I have to decide which one I want to make positive and which one I want to make negative. For this example, I'm going to call B1 positive. The reason why I'm going to call B1 positive is because I'm looking at this and I say I got 3 amps and it's closer to this one, so I think B1 is going to win between the two, but you could do either one as long as you're consistent. So if B1, which is coming out of the page, is positive, then B2, which is going back into the page, is negative. In other words, B2 is going to try to undo what B1 is doing. Now, let's write out our equation. We know that B1 is going to equal mu naught I1 all over 2 pi R1. We know that B2 is going to equal mu naught I2 all over 2 pi R2. We can actually pull out some constants here if you want. We can pull out a mu naught and a 2 pi, and we get an equation that looks like I1 over R1 minus I2 over R2, like this. When we plug in numbers here, let's see what we get. Mu naught is equal to 4 pi times 10 to the negative 7th Tesla meters per amp. Oh, and my units got really fuzzy there, but you know the idea, Tesla meters per amp all over 2 pi. Then I1 is going to be 3.0 amps divided by 0.20 meters minus 2.0 amps divided by 0.40 meters. Plug that into your calculator and let's see what we get. I'm going to try it here. I get you're typing it into your calculator and I'm typing it into my calculator. Isn't it so fun to type into calculators together? Okay, well, here's what I got. I hope this is what you got as well. I got 2.0 times 10 to the negative 6th Teslas. Don't forget about your direction. You have to pay attention to which one is going to win. Is wire 1 going to win or wire 2 going to win? And I say, well, since I got a positive answer and I said that out of the page I defined to be positive, then I can write this as out of the page. Since between the two, wire 1 is going to win and it's going to create a stronger magnetic field. And there it is. Whew, we covered a lot today. Wow! We talked about Ampere's law and we did 2 examples. But before that, we talked about the right-hand rule and how to find the direction of the magnetic field created by a current-carrying wire. We did that for a straight wire. We did that for a loopy wire. We also did that for solenoids. We talked about electromagnets and how electromagnets work. And then we also just kind of covered the concept in general. This is Oersted's principle that says that any type of wire that has a current flowing inside of it is going to create a magnetic field, since all moving charges create magnetic fields. And that is all for today, folks. I hope you have a wonderful, wonderful rest of your day, and I'll see you all next time. Bye, good people.